is from Marcel Moura, Lab in Norway. He will be talking about experiments on transient and steady state flows in porous media, the transition from viscous fingers to compact displacement during unstable drainage flows.
Thank you very much again. I shared the words from the previous speakers. I want to thank the organizers, and we're having a very good time here. Hospitality and kindness since the minute I arrived here. Very happy with it. So this is a very long and bad title that no one will remember, but I'll be talking about experiments, I'll be talking about transient flows, and I'll be talking about steady state flows. And I work at the Porous Lab at the University of Oslo, and this work is done with a bunch of people in the group of Knut Jørgen Monroy there. Okay, so here you have a little video of an experiment. I'll be talking more about that later on. So there will be two parts in the talk. The first one is transient. The second one is steady state. And what you see here is injection of air, in this case, into a porous medium that is filled with another liquid. It's a liquid that's more viscous than air, so that's why you get viscous fingering like that. This is what this type of behavior is called. And the second part is the co-injection of two liquids that do not mix. That's the kind of thing that Alex has shown a little bit before. And since I'm the last speaker, I'll try to grab your attention. So this is a little bit of eye candy here. These are birds. I do not study birds, but I think these are very interesting. I don't know if anyone has seen one of these things here, this big cloud of birds. It's called a murmuration. And it's a very interesting type of collective behavior. You see, like here, there's a predator that's flying around and is trying to catch the birds. And the whole thing kind of like behaves as a single organism. You know, you can see like some waves, propagation, like information waves that go around this thing. I could show this the whole day. It's really interesting. This one here, I don't know where the predator is. It's somewhere there. Oh, there it is, up there. And then it tries to capture that. And then you see like these waves that kind of like tells to the other organism, there is something here, so move away. And the point here is, even if we know everything about one single entity of a system, it doesn't mean that you immediately know what happens when you put a bunch of them together, because complexity arises, and a lot of the things that we deal with has to do with this kind of general idea that when you have like the collective interaction of many particles, whether it's flowing porous media or fracture propagation or anything, new things appear when you try to scale things up. So going from a smaller scale to a larger one is often not easy, and this is also true in porous media. Upscaling is pretty hard, and there's a lot of us trying to understand these things. So this is the pore scale where we understand the physics pretty well. So this is where classical fluid mechanics applies. So Navier-Stokes equations basically for Newtonian liquids. And then to go from here to here, the core scale, the type of scale of samples that people take to study porous materials is already a tremendous job. And then going from there to this scale here, the aquifer scale, this is the Guarani aquifer in South America. There is enough water there to feed the whole world population for something between 200 years to 1,000 years, depending on what kind of like a model for the growth of population you use. So these things are very hard. The experiments that I'm going to be showing are somewhere between these two scales here. And okay, so let's go to the first part about transient flows. And the easiest transient flow, the easiest drainage experiment that we have, we can make it here. If you take a little tea bag outside and you put it on top of a napkin, what you see is a drainage experiment where air enters from the sides here in a big succession of bursts. These bursts are what we call Hain jumps in the porous media, and it's a very characteristic thing of a drainage. That's when you have a non-wetting phase entering a porous medium that is filled with a wetting phase. So for instance, air entering a material that has water inside. So that's this case here. And people have studied this a lot. So here is a little model that we have. It's a single layer of beads, of glass beads. And then if you inject air fast, you get this type of a pattern here. It's called a viscous fingering pattern. And if you do the same thing, you just change the injection speed. So I think here is 4 times slower injection speed. You see that the pattern changed a little bit. Now you have like these trapped zones here. I think that's related to one of the questions that you had in one of the previous talks. So these trapped clusters here. So if you have a deformable porous medium, so this is an experiment where you have like a grains in a suspension in between two plates, and then the grains are what you see yellow there, and then you suck out the liquid from the center, so air enters from the sides. You got this type of a structure here. This is called a frictional finger, and people have studied all this type of different regimes. So what happens here is, since the grains now can move, they are not stuck in place. So suddenly frictional forces are important again. Are important now. And people have studied these things and made the phase diagrams like these ones here. You see, if you change, for instance, basically what you have is like you have a bunch of parameters. You change that parameter, you see what happens with the pattern, and then you try to understand why that is happening. So here, if you go from slower to faster, it's in this axis, and in this axis is more deformable or less deformable. So here the porous material is fixed in place, only the fluids can move. And here is what happens if the porous material itself can move. And different groups have studied this system on varying different types of things. So here is if you vary the wettability of the medium. It was done by the group of Ruben Juanes in MIT. And here, so what we were talking about, it was the work was inspired on this work here by the group of Bischoff-Berger, and she has been studying what happens if we inject the one fluid into a helical cell that's just two glass plates that's filled with another fluid, and then you change the viscosity ratio. So basically, you make you increase the viscosity of the fluid that is entering, or I think she decreased the viscosity of the fluid that's around. But anyway, what matters is the ratio. And what she found is that you go through a transition between the usual viscous fingering type of instability, that's this one here, Safman-Taylor type of instability, that's well known, to something where you have a central zone that's compact with fingers on the outside, if you increase this viscosity ratio. So here there is no porous medium and the fluids are miscible. And then we ask the question, what happens if we have immiscible fluids and a porous medium? Okay, so these are the experiments. So for this experiment here, we are keeping the pressure of air. Air is what's entering from the center, is what's white in the image. So we keep that pressure constant, and then we vary this viscosity ratio. So we basically decrease the viscosity of the liquid that's there, of the darker one here. This is the usual viscous fingering pattern. And then as you increase that viscosity ratio, you start to see different things like this one. And here, very fast, something that looks completely different from that. And what you see is you start to see something somewhat similar to that you have like a zone closer to the center that's more compact. And then you have fingers around that perimeter there. So we saw something similar, and then this was published in the Physical Review of Fluids, and we tried to understand this type of regime here. And that is what we call a compact displacement regime, in contrast with the viscous fingering regime here. This is what the model looks like. So it's about 40 centimeters in diameter. So this is not microfluidics. This is a centimeter scale type of experiments. And we have a bunch of pressure sensors that we put around here. So here I think we use the 5 or 6 so that we can have an idea of the pressure field as well in the experiments. So if you, the 3 experiments that I showed you are these 3 here. And then if we change the injection pressure, we can populate this phase diagram here. This regime here, this is what's called capillary fingering. So that's the domain where capillary forces are important. If things are very slow, and then basically the forces of surface tension is what's governing the dynamics there. And this is the usual viscous fingering case around here. And then if you move that way in this diagram, top left, you have this domain here where you have this compact invasion. So we digitize the image, and we make this call it the invading matrix. So this is just this colorful map here. It's very convenient because with just one image we have access to the temporal dynamics. The color is just the time that a given pore is invaded by air. So it's this kind of like a way to get like a video in a frame, the information of a video in a single frame. And we do the same thing for here, and that's what the type of map that you get. And you can see already from this that you got this type of more circular invasion here, also in time, and the usual fingering structures on this part of the diagram. And we do this, there are 23 experiments that were done here. And another thing that they have observed in the system without the porous medium is what's called proportionate growth. So basically, if you scale up, these are 3 different time snapshots, and if you scale up the picture to fill up the whole frame, you get very similar structures. And we found that in the system with the porous medium, this proportionate growth is also observed on a statistical sense. So here we have defined this outer radius here. That's just the radius of the most advancing finger. And then we have this inner radius here that we call like the RDs, like the dense zone radius here. And the difference between these two is this RF, is the radius of is the finger length. And basically, if we plot the ratio of RF to RD, this ratio for each experiment is approximately constant in time. So that means that if we do the same thing that was done in the model without the porous medium, if we shrink it down, we get similar figures on a statistical sense, not like a really matching one-to-one, but they have like that quantity is preserved. And then something else that we have observed is that the region inside this compact zone is characterized by very intense ganglion activity. And you see here there are 3 points that I marked, one blue, one red, and one green, and they are these 3 points here. This is just a zoom in the segment there. And what I measure here is just like a binary variable. If you have like a liquid, then it's here. If the point there is filled with air, it flips there. So you see that there are some points, for instance, this one here, where it keeps on flipping. It doesn't change state just once. So we can count the number of times that a given pixel flips a state between a liquid field or air field. And we can call this activity order number here. So for that one here, it would be 1 because it flipped just only once. And then this point here, it flipped 3 times. So I give it flipped 5 times. So the activity order for that one is 5. And we can do this for all the pixels. And we get to this type of matrix here, which I call the flipping matrix. And it just gives an idea of how intermittent this dynamics is. It's a bit hard to visualize here because of the color map. So here we have the same information, but on a 3D plot. And you see that now we have X and Y here. This is the geometrical coordinate. So this is the model. If you see from the top, you're seeing like the whole model. And then the height of this mountain is how much that point has flipped its state in time. So we have these 3 things. The information of these 2 is basically the same. It's just a color map here. And this is the invading matrix that I explained before. And we can do this for the whole phase space that we have. And we see that on this region here, that's where we have these taller mountains. So that's where you have more flipping, more intermittent dynamics. So we have characterized this dynamics with this global measure here that gives a probability that a point that has been reached by air will flip again. So this is one number that we associate with one experiment, and that's what you see in the heat map here. And then the points that are marked here. This is the actual experiments, and the rest is interpolated. The data in the background. And we see that as you move towards this region of the diagram, which is again high pressure and lower viscosity, that's where this heat map increase. So that's where we have higher probability of this flipping of states happening. So that's basically a measure of intermittency for the model. And then finally, for this system, we also have pressure measurements. And this is a bit of a complicated figure to explain, so I'm not going to go into details here, not to take too much time. But the main point is this is a spatial time map, and we have the data on these vertical lines here. That's where we have pressure data, and then we interpolate in the rest of the diagram. And if we take a derivative of this map, so we get the pressure gradient map. And the whole point here is the region between these 2 curves, red and blue, here is this they correspond to the area between these two curves here. You see that there is color here, so that means that there is a pressure gradient in this zone here. And for the viscous fingering case, there is no color. This region is dark. So this is what's called the pressure screening, which is very characteristic of viscous fingering, that typically you don't really have a strong pressure gradient between the fingers. So that's why it gets stuck in place there. But in this type of domain where you have the compact invasion, you have a pressure gradient all over. So that explains a little bit the intermittency. Okay, so I'm going to part 2. How am I on time? Not too bad. You don't seem too angry, so I'll continue. Okay, and that's the steady state experiments. So here we are co-injecting 2 fluid phases, and we alternate the injection points. And around this region here, we see that there's a strong influence of the inlet. For instance, around here, you see this part is always white, whereas this part is always blue. But if you look around here, you cannot see the inlets anymore, and you see that it's fluctuating a lot. But you can define average quantities around here. For instance, you could measure the average saturation, the average pressure drop. And these quantities, they are functions of the state of the experiment. So basically like the fractional flow rates and the total flow rates. Fractional flow rate is the ratio between the flow rate of one phase to the other. And that's the type of thing that we want to study here. And we want to characterize this steady state, how it's reached, how it behaves if we perturb it, how it gets back to a steady state. So that's a work in progress. And these models here, the previous type of model that I showed, they are glass beads sandwiched between the 2 plates. This one here, they are 3D printed, so we can have a good control of the porosity and permeability of the model. And this is about this big, more or less. And you see, depending on the total flow rates, you have different flow regimes. So here you see a regime where we have like this intense mobilization of ganglia. And the ganglia are typically larger than the pore size. And then if we increase the flow rate a lot, you get to this type of domain where it's just a bunch of tiny little droplets, lots of bubbles that are typically smaller than the pore size. And this starts to look like a single fluid with a different viscosity. So I expect that in this type of regime, we will be again on the Darcy part of the flow rate curve that Alex explained before. So that means that the pressure becomes, the pressure drop is linear with flow rate, whereas here it's not. Here I'm measuring the saturation in a little box there. And you see that initially this box is completely blue, so the saturation is 1. And then once the front reaches the box, it drops and it reaches a steady state. And one interesting thing that was somewhat surprising to me was that actually it's almost like a steady state front that is approaching a zone that is filled with just one phase. It really does not take very long for a steady state to be reached. It's almost like a shock wave of a fluid that comes almost already at steady state. And so we are investigating this by changing the conditions. So here it's, let's see, it was a water flow rate and a silicone oil flow rate. So I just increased them both a lot here. And you see a completely different regime there. That's lots of tiny, tiny drops. And again, like the steady state is reached very fast. And then it fluctuates on top of that quantity. So one thing that we're trying to do here is to measure the entropy of this type of system. So this is in line with what Alex explained in the beginning. It's a Shannon type of entropy here. So it's the sum of a P log P over the configurational space. And one question is if this entropy that depends on the flow rate, on the pore area, and on the area of the wetting phase, so that's basically saturation, if that can be split into 3 different separate components. And I'm not going to answer that, so we're investigating this type of thing, but I'll be focusing on this one here, which is what we call the configurational entropy. So that's it's just dependent on the wetting phase area. So what we have, this is one of the pictures of the experiment. So we just digitize it. So here, black is solid, green is oil, blue is water. And here we have time So we have a bunch of different frames like that, one on top of the other, like this. And we can make a cube like that, where this axis here is time. So this is a space-time matrix. And we can have cuts in this matrix in this direction here. So for each fixed position x, we have one of these barcode looking type of things. And here is it's showing like what's water and what's silicon in that specific line. So in that position of that line here. So each position of the line would correspond to one of these plots there. So what we can do is to integrate in this direction here to get the total amount of water as a function of time, as a function of the frame number. So that's this plot here. I'm just summing in this direction and then flipping it here. So you see that the amount of water, it fluctuates as you expect in time, like that. So you can measure a probability distribution function of these fluctuations here. And that's what we get there. And then from this PDF here, we define an entropy, a configurational entropy of that slice as a sum of P log P, where the probabilities are measured from this histogram. Okay, so in the end, with that, we can have the entropy as a function of position inside the model. And that's what we get. So that's this curve here. And what we saw is that, so the 0 here corresponds to the inlets, and that point here is mapped here. So as you go into the model, this entropy seems to increase and then fluctuate around some well-defined steady state. And then what we want to do is to understand how this entropy is a function of the properties of the system, and try to see if we can move forward with the experimental verification of the quantities that Alex has shown in the beginning. So can we take derivatives of this type of thing, for instance? So we can measure a probability map for the filling state of the pore. And this answers the question, if we look at one fixed position here, we don't know any information, but if I look at that position of the system, what's the probability that that point is filled by one phase or the other? And that's done by just projecting this type of a diagram here on the X and Y plane. And you get this type of map here with colors. The colors is the probability. So 0 means that we would never have water at that point. And then red is that the point is always filled with water. And then you see that there are some channels of very low probability of having water. So that means that most of the time it's the other phase, it's the silicon phase that's flowing through these channels. And regions where you have very high probability of having water. So for instance, around here, it's most likely a little trapped cluster because the pores are very small. So there is very high chance of having water there. And this thing here, if we zoom in, we see that it has structure. Or we want to try to correlate this structure with the pore structure to see if the distance between two cylinders is small, does it mean that the probability of having water is large or not? So this type of thing is what we're going to be doing next. We can compute this probability map also in time. So if we have just like one frame, for all the information that you have is one image, then you can only say associate probability 0 and 1, 0 where there is no water, 1 where the water is. And then if you add more frames, you start to build up this probability map. And it doesn't take long for it to stabilize. So one thing that I want to try to do is to see if we can measure this thing dynamic in time. So for one time, get a probability map of having given phase there, and see how this probability changes, if it does in time or not. All right, so the conclusions. So from part 1, we have observed these transitions between viscous fingering and the compact displacement. And for low viscosity and the high pressures, the structure presents a proportionate growth. We still don't have like a proper explanation as to why that happens. We just observed it. And we introduced two quantities, this invading matrix and the flipping matrix, to characterize the dynamics. And there's very intense ganglion dynamics inside this compact zone, and the pressure screening is very much reduced. So basically there are pressure gradients there this is different from the viscous fingering state where we don't have that. And for the steady state, we have measured this configurational entropy, and we are studying like how it evolves with the conditions of the experiment, and we also obtained this probability map. And I have a couple of minutes, not much more, so I just want to mention these two projects here that we have been involved with. So these experiments and simulations, they're very nice to look at, even if you don't care too much about the science, just like from the aesthetics of it is very interesting. So we made this little gallery here that you can walk around and like see some pictures of the experiments on the internet. So if you are interested, you can find it on the website of the group, porelab.no. And then last year, Alex and I got involved in a bit of a crazy project with some artists and an art curator in Romania that are very interested in collaborating, like the boundary between science and art. So we had an exhibition with some artwork that was based, made, inspired by things that are done by the group. It's called Porous Matter, and there is a website too. This one here is a very interesting work. It's basically like the capillary bundle model that an artist made, her interpretation of it. So that went very well. So just to finish, this is a frac meet, so I thought I should have at least one fracture somewhere, because I don't really work much with fractures, but I want to put this one there. And also inspired by the previous talk. So this is a fracture network that appeared in one experiment. I have no idea what's going on here. It's just a drying pattern. But then there were like some glass spheres, and I found it really interesting because they kind of like acted as focal points for these patterns. So I don't know what's the VN combinatorics of that one, but it showed up. Okay, I'll stop here.
Thanks very much, Marcel, for this interesting talk. I think the two last talks of this afternoon had to do with art in addition to science, definitely. So we have some time for questions and comments. Do you have any question? Actually, I have one, because Alex Hansen taught us about this co-moving velocity concept, which was central to the theory. But I understood that in your experiments, you drive the two fluids from the same site in the same direction. Do you take into account that co-moving velocity?
We want to try to measure it. So the experimental measurement of that is it's not very straightforward, but we want to try to measure that. We need to make many of those experiments to calculate the steady state value of the saturation, and then vary the fractional flow rates and the total flow rates, and then the co-moving velocity will come as a derivative of this map. But it's not something that you can just like make one experiment this way here and get the co-moving velocity there. So there is a way to get it from the relative probabilities, but that's not how I'm trying.
So part of my question was, would you be able to drive one fluid in one direction and the other in the other? Does it make sense? And so as to have the co-moving velocity equals 0 or something like that?
So this co-moving velocity, like the intuition around it is not that simple. Like to go with like different directions, I don't think that necessarily means that the co-moving velocity would be 0, right? Alex is the person that's best to answer this type of things, but it's the name is a bit it's a bit we don't really yeah.
So okay, so we should not understand it as the co-moving velocity in classical relativity theory, but something else, huh? So we have some other questions, please.
So the beads that you are using, do the nature of the surface matter, like which fluid like it?
Yeah. So they are water wet, so that matters. The beads, they want to be wet by the fluid that is there, the dark stuff here. So they're glass,
No, but my question is in the context of two fluids. So whether one fluid has more affinity to wet surface.
Yeah. So like here, like the blue one is it's more. I mean, the wettability. It's the system is more water wet than oil wet. So the water is the blue one. But it's not as great a contrast as it is in the case of the glass beads, because the glass beads, like, it's really very water wet. If you were to measure like the contact angle of a little drop, it's very small, like a 15 degrees, 20 degrees. In this case here, it's more around the 60, 70 degrees. So it is slightly water wet. Okay.
So my question is that your Helishaw cell is like you are injecting air or the fluid from the center of the glass. Suppose you could also, we did experiments where we had two glass plates which had the more viscous fluid in the middle, just a drop of paint, and then we lifted it vertically and air invaded, forming viscous fingers. So, so the pattern is slightly different. Did you try something like this? The statistics that you showed, do you think?
We are doing that on a separate project on a rheometer. You know, like a rheometer is basically two plates, and like what was shown, like on the first talk was shearing, but we are lifting that,
Lifting it, yes,
and then seeing like the air that enters from.
That's also viscous fingers, but some fingers get sort of stopped because as they move forward, they start fighting for space because the space available is. So their nature would be completely different. I mean, you could check that, number one. And number two, I was just in a question answer, I mean, to somebody who asked, I suppose this is just a question to you and Alex and everybody else here, that I think Bodhi asked himself, that if we place some fluid which is having intermediate viscosity, let's say you have higher less viscous moving this side, and you want it to be on the opposite side, right? So it has to be even less than that. Yeah, no, I don't think so. I can't think of an arrangement like that. Yeah, but it's interesting, yeah, to say. Okay, thanks. Nice.
Thank you. Other questions? If not, let's thank all the speakers of this session, including Marcel,